Hello everyone, and welcome to the Gearing Up training for how to create and teach coding activities. The information in this presentation is targeted towards the grades 5 to 8 range, but most of it should be generalizable towards older and younger audiences as well. Okay, let's get started. First off, why is teaching coding something that we want to do? Well, learning how to code allows you to give instructions to a computer and solve problems which would be difficult or impossible to solve on your own. The better you are at coding, the more flexible you'll become, allowing you to solve many more types of problems and interact with the digital world in new ways. We also want to increase the diversity of people involved with computers and technology. Learning how to code has a reputation of being an intimidating and a difficult process, and many people count themselves out because they don't think they fit the image of who a coder is. Personally, I've always struggled with math, and because of that, I didn't think I could learn how to code. It wasn't until my grade 11 year, where I had a math teacher who encouraged me to try it, that I figured out I enjoyed coding and was actually quite good at it. So, if we can expose students to coding in a playful and exploratory way, then we will get more people interested in the topic when they otherwise would not have been, especially if we can do it at a young age. It doesn't matter who you are or where you come from, anyone can learn how to code. Finally, coding is a great way of teaching general problem-solving skills. A lot of the strategies utilized in coding can be generalized to nearly any problem, and because computers give you such fast feedback on whether or not your solution worked, it's a great way to train your problem-solving skills. So when we teach coding, what are we actually trying to teach? Well, one answer to this question could be, we are just teaching students how to write code. But the problem here is that there are so many different coding languages we could choose to teach, and there are new languages and frameworks being created all the time. So it just isn't possible to teach someone every coding language they might need to know. But I'll let you in on a secret here. The actual language we use to teach doesn't matter, because we aren't actually trying to teach a student how to write code. Instead, we're trying to teach the more general skill of computational thinking. What exactly is this? Computational thinking is a type of problem solving which involves expressing problems and solutions in terms which can be understood and executed by a computer. Basically, through learning how to think computationally, you are learning how to speak to and understand computers. Computational thinking can be broken down broadly into 4 steps. First, we have decomposition. This is the process of breaking problems down into small enough pieces until each piece becomes small enough that you can figure out how to solve it. We also have pattern recognition. This is being able to recognize that there is some kind of pattern here, looking for similarities and differences, wondering if some steps are repeated. We also have abstraction. This is where we ask ourselves what the important and relevant details of a problem is. Sometimes there are more general versions of the problem, where we might be able to solve multiple different types of problems using the same solution. Or sometimes we'll have a similar solution that we used in the past for a different problem that we realize we can reuse most or parts of for the problem that we're dealing with now. And finally, you have algorithm design. This is where you're taking the abstractions and your thoughts about the problem and you're actually turning them into concrete instructions that a computer can understand. These instructions are going to be specific to the technology or the language that you're using. So how would we actually go about teaching computational thinking? Well, the answer here is something called inquiry-based coding. It's the same idea as any type of inquiry-based learning, where the student is put in the driver's seat and is allowed to let their questions and curiosity guide the learning process. As an example, let's say that you wanted to make a simple game that involved using the mouse to move a ball through a maze with the goal of getting to the green circle at the end of the course. One way to teach this would be to stand at the front of the classroom coding on projector and getting the students to follow along with everything that you write. This might get them to the end quickly, but they would lose out on a lot of the important learning. Instead, we can let the students start with a blank game and let them figure out the problem by utilizing their computational skills. They would then have to break the game down into its smaller pieces and tackle the problems one at a time. Instead of giving answers, the teacher's job here is to gently guide the questions. A general approach to teaching inquiry-based coding can look like the following. Start by introducing the class to a single concept or tool. This can be something like how to use an if statement in Scratch. Having a few examples of this that you go through together can give the class a starting point to work off of. Next, you can lead the group through a short tutorial that uses this concept or tool. Sometimes it's nice to just get a little bit of guidance at the start of a session to get you started with something. After you've done that, you want to give time for an open-ended challenge. This is where the students really get to practice this skill of going off on their own, identifying a problem and breaking it down by themselves. And finally, it's great to just encourage collaboration and sharing. A lot of the time, students might know how to solve problems that you don't know. They might want to work together to solve problems. You should encourage all of this. It's a great way to learn how to code, as well as be a team member. We can contrast inquiry-based coding with recipe-based coding, which can also be known as repeat exactly what I do. While this style of teaching can be useful for learning how to solve a specific problem, in the real world, students are going to come up against problems that don't have an existing solution. And with how fast technology changes, the exact way you give instructions to a computer is constantly changing. So learning how to copy down exact instructions isn't super helpful in the long term. It's unlikely that any activity you do will completely avoid this type of instructions. As with code, there will always be finicky sections in which students need to be specifically guided through. It's a style that you should try to minimize as much as possible while maximizing inquiry-based coding. If we hop back to our graphic on computational thinking, we can illustrate this concept more clearly. When teaching programming, it's easy to focus a lot on the fourth step and leave out the other three. What's so great about this type of problem solving is that it goes beyond computers. The first three steps are incredibly useful for any type of STEM or engineering problem. Coding is just problem solving using code as your tool. And I think especially with new technologies such as large language models like ChatGPT, it further emphasizes the importance of being able to think through a problem in an abstract way, as opposed to just being good at writing algorithms with code, as these technologies are automating increasing amounts of that fourth and final step. So you might be thinking, okay, this inquiry-based coding sounds fun. What happens if a student gets frustrated or gets stuck? How can I help them if I'm not supposed to be telling them how exactly to fix their problem? Well, this is where the process of debugging comes in. Debugging is what we call the process of fixing problems with computers. You can start out by hypothesizing what could be going wrong. This involves looking at the problem and thinking about what could be causing it. When you have some ideas about what could be going wrong, you can start testing those ideas one at a time. This involves making a change to the code and then observing the result. Finally, you'll evaluate the progress. Did your change fix the problem? If it didn't, you might need to head back to the hypothesize step and think more about what could be causing that problem. Each time you repeat the process, you can gradually narrow down and isolate what could be causing the problem and slowly puzzle out a solution. This process can feel challenging and sometimes frustrating, especially as a beginner. But interacting with computers takes patience, and debugging is an extremely important and valuable skill to learn, one which can be generalized far beyond just interacting with computers. Throughout my explanation here, you might have thought, hey, I recognize this process. It looks very similar to the scientific method, and you would be correct in saying that. Debugging is very similar to doing scientific work of any kind, as you're trying to locate, isolate, and solve the cause of a problem through observing the effects that it has. In fact, coding with computers is a great way to learn these skills because of the nearly instantaneous feedback you receive, allowing you to iterate through your thinking many times faster than you would in many other scientific contexts. In classrooms, a great way to teach coding is through the use of pair programming. Pair programming is where two people will sit next to each other and will work together to code using the same computer. This is a great way to reduce the number of errors made during coding, as you can have two people working to catch and fix errors before they become critical issues. It's also a great way to teach teamwork and communication skills. So how it works is that you give each person in the pair a separate role with their own responsibilities. The first role is the driver. This is the person who will be in control of the computer, and the one interacting with the mouse or keyboard or screen to actually write the code. This person's main job is to be thinking, what do I need to write to solve this problem? The second role is the navigator. This person's role is to be a second set of eyes to help with errors and think of the bigger picture of what's going on. They might ask questions like, are we solving the right problem? Or what issues might arise in the present or the future with the code that's being written? In the coding activities, you'll want to assign the roles initially and make sure that you're getting the students to swap roles regularly, making sure to give them about the same amount of time for each person for each role. Now that we've covered the why and the how we teach when we run coding activities, let's dive into what we teach. What are the specific types of activities which tend to work when teaching coding? The undisputed champion here is video games. They tend to offer a lot of flexibility and are inherently fun and engaging for students. Next, we have sensor-based activities. This is where you start using more hardware and are using that to gather information from the world somehow. Finally, we have robotics, which are a bit of a mixed bag. They're very polarizing in that they tend to either go extremely well or extremely poorly depending on the number of bugs you face. But let's dive into more depth with each of these, starting with video games. Why is this something we want to teach? Video game creation is a fantastic medium for learning how to code. This is what first got me into coding, as well as many other people. Here are reasons why using games to teach code work well. First, they're really fun and engaging for students. It helps you turn something entertaining into something that's educational. They're really great at creating a sense of accomplishment. They're also a very creative way of learning coding. There are many different ways to make a game that can pull you away from this recipe-based coding or just following a step-by-step guide and move more into the problem-solving inquiry coding that we want to teach, because that's more similar to what a coding career is like. It's also very modular, so the game can be very simple and you can build onto the games with more and more layers for advanced learners. So it allows students of all different levels to come into the activity at different points. And finally, many students play video games in their free time or have at least tried them before, so they understand what pieces are going to be in a video game already. Because of their inherently play-based nature, games are a great way to smuggle learning into something fun. It's a little bit like when you're trying to get your kids to eat their veggies, you might want to repackage it as something like a smoothie or a burger. Games also have a high chance of giving students learning that they can take home with them. A lot of people play video games in their free time. So learning how to make games also gets you questioning how your favorite games were made, forcing you to think and stretch your brain a little bit while having fun at the same time. Finally, teaching coding through video games is great because games combine design and technical aspects together into a single project. Some students might want to dive deep into the algorithms and math and focus on something that is highly technical, like a game with realistic physics. Or they might go completely to the other side and get deep into the design and end up with something that resembles more of an interactive piece of artwork as opposed to a traditional video game. They also could land somewhere in the middle, where they still want to create a game, but they focus on the interactions the player has, or the characters and the visuals and the story. All of these approaches are valid, which is why video games are excellent for teaching with inquiry-based coding. It allows the students nearly infinite flexibility to come up with their own project and drive it into areas that they have a personal interest in. Video games are by far my favorite tool to teach with, and if you are going with a purely software approach to teaching, these should be the tool that you are using. It can be tempting to create more real-world applications, such as building a calculator, but these are almost always going to be less flexible and less fun than making a video game would be, while also not teaching enough different skills to be worth the trade-off. Next, we have sensor-based activities. These can be a lot of fun, as they are typically much more hands-on and physical than video games are, and can involve going outside into your local community to take and collect data. An example of this would be an activity in which you could use microbits to measure the angle that they're pointed at, and with some help from some basic trig, you can use this to calculate the height of various objects in your community, like trees or buildings. But these activities are inherently more rigid than game-based activities, as there's typically a single correct version of the code that needs to be written. You can get around this by pre-building parts of the code for the students, but you are inevitably going to be relying more on the recipe-based repeat after me teaching than you would with a video game. Sensors can also be tricky because you introduce hardware into the equation, and this can be another source of error. This makes it more difficult to track down bugs, as it isn't always obvious if something is being caused by the hardware or the software. Finally, we have robotics-based activities, which are by far the most difficult type of activity to pull off successfully. The following advice comes from my experience from teaching these activities, which include many years of teaching in a university robotics lab. One of the main issues you'll face here, especially with children, is a huge gap between expectations and reality. A lot of people have their perceptions of robots colored by fiction, which are an interesting way of learning what robots could be like one day, but they are not like this in reality. There is a reason that we don't see robots walking around in our society. There is a reason that self-driving cars are still mostly a proof of concept. This is because robotics are extremely complicated and finicky to work with. Moving around naturally and interacting with the physical world is something that humans can do very easily, almost subconsciously. But for robotics, even very simple tasks like driving in a straight line can be extremely challenging and frustrating to make work properly. As soon as you start adding in more behavior like avoiding obstacles or picking up an object, things scale in complexity extremely fast. A lot of this is because there are going to be errors with both hardware and software, and pinpointing these errors can be extremely frustrating, even for a classroom where both the teacher and the students have a lot of experience. You can quickly run into a situation where more students need teacher help than you have teacher time to give. Now, all this doesn't mean that you shouldn't run robotics activities in a classroom. What this does mean is that you need to keep it simple. I recommend separating out hardware and software into two completely different types of activities. So the first option would be buying pre-built and professionally manufactured robotics, and then just coding the software behavior for those. This will eliminate many, though not all, of the hardware errors that you encounter, and you will likely find that getting autonomous actions to work is still quite difficult. The other option would be to build your own robots, but then stick purely to direct human controls, so no autonomous actions at all. This will greatly simplify the software side of things and allow you to focus mostly on debugging the hardware. I would only recommend the second of these options, though, if you are comfortable in your knowledge of hardware and electricity. If you can pull off a robotics activity, they can be some of the best learning experiences out there. But there's also a high chance of critical failure, where the issues pile up so fast that no one gets things working, you don't have enough time to help anyone, and you end up having to abandon the activity entirely. So tread carefully and make sure that you thoroughly test any robotics activity that you plan on running. So to wrap it all up, let's go through the process that you might follow when creating a coding activity. First up, go into it with the mindset of reducing the complexity. This is particularly advice for those who are watching who are experienced coders. It is always better to undershoot the complexity and the difficulty of an activity than to overshoot it. And it's very easy to accidentally overshoot. Ideally, your activity should have a low floor but a high ceiling, meaning that it's easy to get something working, but there's lots of room to expand and make things more difficult for those that choose. Again, video games tend to excel at this. Second, think of the idea or theme that you want to teach while coding. You can find this theme by working top-down or bottom-up. If you do it top-down, you'll want to have a topic area, a unit, or theme that you want the activity to fit into, such as sustainability or visual art. Or you can work bottom-up by choosing a specific technical concept that you're interested in teaching, such as if statements or loops. Next, you want to do some research into the area you choose. There's a good chance that somebody out there has already created something that is either exactly what you're looking for, or close enough that you can use it for inspiration. If you choose to do a pre-built activity, that's totally fine, and it may even be the better option if you aren't as experienced with teaching or creating coding activities. After you've chosen your topic or idea, you've done some research, and you know what you want to make, then the next thing is to start writing the code and making the activity. This step won't apply to you if you're using a pre-built activity. You'll want to build out the full activity here, completed with everything you want the students to do. You'll want to keep track of which areas are difficult or easy when you're doing the building, and pay attention to what knowledge your students possess and what you'll need to teach them. When you're done building your activity, you'll want to thoroughly test it, ideally by using people other than yourself who are at the same level as your students. This is one of the most important stages because you do not want to be testing out a coding activity while you are running it for the first time. Especially if you are an experienced coder, it's easy to think that the steps along the way will be easy, only to realize that there are places where the students have no idea what to do. Finally, you'll want to refine and reimagine your activity as needed. Every time you run the activity, you'll always be able to find ways to make improvements. Best activities are the ones which have already been tested and run in classrooms multiple times. That's it. Thanks so much for listening, everybody. Hopefully you found this video helpful and you are able to use it when you're designing and teaching coding activities in your classroom.